Hello. We still continue with taking up theorems on under circles. The next few theorems are all on the similar note of proving using congruency of triangles. So we'll just be discussing these theorems without actually completely solving them, so that we can move on with more questions. I'll just be discussing how to go for the solution. The theorem says two chords AB and AC of a circle are equal, right? Prove that the center of the circle, I made a spell mistake here. The center of the circle lies on the angle bisector of angle BAC. How is this done? Let me draw a figure, a circle. There are two chords, AB and AC. This is suppose AB, this is AC. This because they are equal, it's given to us. I also will have to draw the angle bisector. The center might just be here somewhere, and I name it as O. I also will join this point BC because I have to make the angle bisector pass through the center, and this point of intersection I might write as M, or you can write D, whatever. What do you actually have to prove is AM is passing through the center O. If we can prove that AM is the perpendicular bisector of BC, that can help us prove, because a perpendicular bisector of the chord will always pass through the center. So we look forward to prove that AM is the perpendicular bisector of BC. That's the basic catch of it actually. If you prove AM is perpendicular bisector of BC, that you can do always taking the congruency of the triangle AMC with AMB. Okay, I can simply write here, the first step will be proof of triangle. You can try by yourself this one, because in the previous sessions we have seen how to prove the congruency of these two triangles in many cases. AMB. Once you prove the congruency of these two, second part will be by CPCT. You can say that angle BMA is equal to angle BMC, thereby taking these two angles a linear pair, you can go on to prove that angle BMA is equal to angle BMC because they are 90 degree. Now this is what we have already proved. Okay, AM is perpendicular to BC. Herein you can write, since perpendicular bisector of a chord always passes through the center, AM also passes through the center, right? Now let's take up one more. We move on to another screen. I write the statement first. It says if two chords, is just I think the converse of the previous one. If the two chords A, B and AC AC of a circle with center O are such that the center O lies on the bisector of angle BAC, prove that AB is equal to AC. That means we have to prove that the chords are equal. So here in the bracket I can write the chords equal. Oh, it didn't fit in there. I can write it here below. It says the chords are equal. So I draw a figure. Oh, do look. I also have to draw two equal chords because later on we need to go and prove the same. Here is the center, is converse of the previous one. So again I will discuss as I did the previous statement. It's AB, this is AC, with this the center O. We draw the bisector of angle BAC. I again name it as M as I did for the previous one. It says so, of a circle with center such that the center O lies on the bisector of angle BAC. Yes, we have to prove that. It's not necessarily that I draw it till here, because it's not about bisecting BC. It is about, I can join this too, because it says the two chords of AB and AC are such that O lies on the bisector of angle BAC. Once I draw the bisector and it intersects at this point with the center, we can stop there. Now let me write what is given and what is to be proved. It is given to us that A and B are the chords of the circle, that we don't need to write. But it says this O lies on the angle bisector of angle BAC. That means angle BAO is equal to angle BAC. These two are equal. Right? Okay. And also obviously it is given that AB and AC are two chords of the given circle. Herein we take, what do we have to prove? We have to prove AB equals AC. That's, they are asking us to prove the chords equal. We have already joined OB and OC. Here also we can, if we prove the congruency of these two triangles like AOB and AOC. Let us start the proof here. In triangle AOB and triangle AOC, it's quite visible that OA is equal to OA. That means OA is common. Now we have to derive something from the other information given. See, if this angle is given equal, look at OA is equal to OB. I separately take this part here. Look at the triangle OAB or AOB. I'll write AOB as I have taken there. AOB. See, OA is equal to OB, right? That's the radii of the given circle. angle opposite to equal sides will be equal, thereby making angle OAB equal to angle OBA. This is, I can write, angle opposite to equal sides are equal. Done. Similarly, in triangle, look at the triangle, the other one, that is AOC. Again, OA is equal to OC for the same reason that they both are radii. Here also, angle OAC will be equal to angle OCA. You can write the same reason here, that angle opposite to equal sides are equal. It also informs that this line OA is the bisector of angle BAC. So we had already mentioned that angle BAO is equal to angle BAC. Therefore, angle OAB will also be equal to angle OAC if I have this, supposes equation 1, this supposes equation 2, and this supposes equation 3, or you can simply write it as BAO as well, as I have written in the given portion. So what do we derive? We would derive, yes, we can derive angle OAB to be equal to OAB will be then equal, I can write it here, angle OAB will be equal to angle OAC, and because we had informed about these being also equal, so the third angle which we that remains is angle OBA will be equal to angle OCA. Therefore, applying AAS congruency, we prove the congruency of these two triangles. We write AOB congruent to triangle. I had written AOB here and AOB here again. It will be AOC then. Sorry, that was my mistake. AOC right here. So that would now take me to the proof, triangle AOC. Once we prove the congruency of these two triangles by CPCT, we can say AB is equal to AC. This is by CPCT. That's what we were supposed to prove, and therefore AB and AC are two equal chords. Thank you.